So I think it's just about 5 after. If we want to get started, Deanna, with some introductions.
Okay, thank you, Jamie. Hi, everyone. Thank you for coming to this seminar. I'm introducing our guest today. Ariane was unable to be here. And because I suggested Zahra as a speaker, I'm here to introduce her. So Zahra Ghodsi, she's a PhD candidate at New York University. She's a recipient of the AI Research Fellowship from JP Morgan and the Ernst Weber Fellowship from the Department of EC there at NYU. Her research interests include designing efficiency systems for machine learning. Before joining NYU, she received, actually before becoming a PhD candidate, she received her master's degree also from NYU and a bachelor's degree from Sharif University of Technology. And just a bit, she is actually my academic granddaughter because her advisor, Professor Siddharth Garg, is one of my former PhD students who is now a professor at NYU. So it's a pleasure to have Zahra here. She's gonna describe her work at the intersection of machine learning and secure systems. So Zahra, go ahead.
Thank you so much. Thanks, Diana, for the introduction. I'm very excited to be here. Thanks for the opportunity. I'm looking forward to share with you my work in frameworks that we designed for outsourced neural network computations. And I'd like to thank my collaborators at NYU, Akshat, Maria, Brandon, and my advisor, Siddharth. Okay, so of course, we know that neural networks have outperformed a lot of previous solutions in a wide array of applications, such as autonomous driving, medicine, finance, etc. But when we look at the design space of these systems, usually it's quite complex. So you would have certain parties with the training data, you would have other entities that hold the test data, some organization might want to use the model that is held by another entity to perform, for example, inference. Or it could be that a client doesn't have the computational or energy resources to perform an inference computation and wants to outsource this to a server. And this creates a very complex web of trust. And the question is, can untrusted parties collaborate in this setting of machine learning computations? So what I'm going to start with is the recent work, CryptoNAS, that is going to appear in NeurIPS this year. And we looked at designing models specifically for private inference. And then I'll talk a little bit about our previous work, SafetyNets, which appeared in NeurIPS 2017. And in that work, we were looking at verifiable outsourcing of deep learning. In the setting for private inference, you have a client with an input data who wants to perform inference on a model that is held by a server. So in this setting, the client's input is private, and the server's model is sensitive as well. So at the end of this computation, the client shouldn't learn anything about the server's model, and the server shouldn't learn anything about the client's input. This can be done with tools that are available in cryptography known as secure multi-party computation. The famous example in that field is the millionaires problem, where you have two millionaires who want to compare their wealth and figure out who has more. But either of them doesn't want the other one to know the exact amount of their wealth. And this problem was formulated by Andrew Yao, who proposed a protocol called Yao's garbled ticket. And the idea is you turn the computation into a Boolean circuit, and then one of them would encode this circuit, and the other one would evaluate it. So at the end of this computation, they will be able to get the result without any of them learning any other's party's input. And this protocol works particularly well for types of computations that are done over bit values. For example, comparisons are quite efficient to be done securely with this protocol. There are other tools such as secret sharing, where each party holds a share of a circuit. share of the secret. So collectively they can reconstruct it, but each of them would only hold a seemingly random value. And this would work well, particularly for linear computations, for example. And another tool is homomorphic encryption, where you're performing computations over encrypted values. So there are all of these protocols, and each of them would work well for certain computations and not that well for others. So if we want to apply these for the types of computations that you have in neural networks, some of the more promising solutions come up with hybrid protocols, where, for instance, you for a function that you have performing inference, where the model parameters are done by the server or held by the server, and the input is held by the client. For the linear layers, you would use something like secret sharing, and for the nonlinear activation, for example, ReLU function, you would use the Decouple circuits. So a combination of these two would enable you to basically do the end-to-end inference securely. But if we look at the runtimes, it turns out that with a lot of these protocols, you have a bulk of computation that can be done offline, pre-processing, that is independent of the input. So in this case, the majority of the linear layer computations can be done offline. And the bottleneck for the online runtime would actually be the secure evaluation of the nonlinear layers. So if we look at the relative costs, online runtime costs of doing a convolution layer, let's say, followed by a nonlinear ReLU, it turns out that the bottleneck is actually evaluating the ReLUs, which can be orders of magnitude more expensive. Now, this is in stark contrast with what we have in plaintext inference, because over there, the majority of the computations is spent on evaluating the linear layers, and ReLU nonlinearities are effectively free. So this made us believe that models that are exist are probably not suitable for private inference, and that intuition turned out to be true. So if you look at the design space of neural networks, usually the goal is to find the best performing models over MAC operations or floating point operations, right? So usually we are looking for this Pareto curve over accuracy, and to find the best models for a budget of MAC operations. Now, what we want to do, this is because, of course, the MACs are costly, and nobody really thinks about nonlinearities. What we want to do is look at finding the best models for the ReLUs that are the bottleneck, because in this case, for the online runtime, the linear layers are effectively free. So in contrast to the previous work, our goal is to find the best models in this space. And that's what we're going to do. So as I said, our intuition was that the existing models use ReLUs indiscriminately, and that turned out to be the case. There was a lot of redundancies in either existing families of models and also neural architecture search methods. So we designed a set of optimizations to construct ReLU efficient networks, and then coupled this with an architecture search method to find the best networks that would have the highest accuracy for a given ReLU budget. So I'll introduce some of these optimizations that we add, and then I'll go over our method for designing the networks. So if you look at the way that, for example, skip connections are designed in a network, let's say we want to add a skip connection in the second layer. What skip connections would do is you're forwarding the values of a previous layer to this to increase the capacity of your model. And in this case, we were looking at the skip connections in ENAS, but the same observations also hold for families such as DNNS. So the way that skip connections are constructed in ENAS is, let's say we want to add a skip connection at this second layer from the layer before this LI. So we add this blue block here where we're concatenating the output of the second convolution with the first layer, and this concatenated block would go through nonlinear layers and then a one-by-one convolution, which would reduce the channel size back to the original size. So if you look at this added block, which was included for this skip connection, we have added a lot of nonlinear layers, this large number of ReLU, additional ReLUs for this concatenated block. This is not optimal. As I said, the ReLUs are the bottleneck. So let's take a closer look at this. So the two inputs to this one-by-one convolution, the first one is the ReLU value of the second convolution. So we can just move this ReLU operation here. This is the same function. Now, if you look at the second input to this one-by-one, this is the ReLU value of the first layer. But we've already done this computation at the very beginning. So instead of this redundant ReLU, we can forward this value of the layer from a point afterwards, and feed this directly into the convolution. So in this case, for this block of a skip connection, we've reduced the number of ReLUs by a factor of 2. In this case, without changing the functionality. So this is a case of the redundancy that exists in the design of neural networks, and we want to make sure that we get rid of all the such cases. So this is what we call a shuffled skip connection. Again, this keeps the same functionality, but reduces the number of ReLUs. Additionally, you can further prune ReLUs. So in this case, in the skip connection, we can get rid of this additional ReLU that was introduced. Now, this would change the functionality and potentially affect the performance, but because we're looking at this Pareto curve, we're looking to find the best models for a given budget of ReLUs, this is eventually going to help us. So this is a family that we call the Pruned skip connection. In this case, you can actually add skip connections for free, meaning that they are not going to add any cost to your, in terms of ReLU, number of ReLUs. And the final optimization that we introduced relates to balancing the number of ReLUs across layers. And so let's see what I mean by that. Conventionally, in the design of neural networks, after each pooling layer, the resolution of the layers is reduced by a factor of 2, and the number of channels is doubled. So what that does is effectively balance the number of flops at each layer. So keep the number of flops the same at every layer, because flops are proportional to h squared c squared. So there are different reasons you might want to do this. As an example, if you have like a hardware designed for performing these computations, you want to maximize the use of that hardware at each layer. So you want to distribute this computation evenly across all of the layers. And this was like a conventional design choice for a set of families of neural networks. But because we are interested in finding the best networks for a fixed ReLU budget, we replaced this with a design rule that balances the number of ReLUs across the layers. So what that means is that at each pooling layer, when you reduce the resolution by a factor of 2, you want to quadruple the number of channels. And that is because the number of ReLUs at each layer is proportional to the size of the activation matrix, which is H squared C. And we show in the paper, we have like a small proof that shows that if you assume that the capacity of your model is proportional to the trainable parameters and number of trainable parameters, then to maximize that for a given ReLU budget, you want to distribute the number of ReLUs evenly across the layers. So the models that we design in CryptoNAS are going to be all ReLU balanced. So for the same budget, actually, for the same ReLU budget, the models that are ReLU balanced are going to be larger. They have more parameters, but because the bottleneck for us is the number of ReLUs, we don't care about the added overhead of flop computations. Okay, so just as a reminder for people who might not be familiar with, recently a line of work has been introduced in automating the design of neural networks. And the idea is that you train a controller which is going to sample architectures. For example, depending on the design space, you can have determine the number of layers, operation at each layer, etc. So this controller can sample a number of potential architectures. You can train these architectures and use the validation accuracy to further update this controller and do this iteratively such that the controller learns the best architecture. So instead of manually designing these networks, you want to automate this process. And we were looking to use this method to find the best networks that would perform best for private inference. And an example of that is ENAS, which for the macro search, it finds at each layer what operation to use and also where to place these skip connections, basically. So how did we go about the search for these best networks in CryptoNAS? So we first designed a set of base networks, which given a depth and width would give us, would basically determine the number of ReLUs, and depending on the size of the network, you can get different accuracies. And then on top of these base networks, we find the best skip connections, the placement of these skip connections, which would further increase the performance of these models. But because of the optimizations that we introduced, these skip connections are effectively free. So you can have your best network determine the number of ReLUs and then further increase the performance of the model by this addition of skip connections. So effectively, we are decoupling this search into finding the optimal base networks and then finding the optimal placement of these skip connections. So for designing these base networks, we followed some of the conventions that exist in designing neural networks. We place pooling layers at 1/3 and 2/3 of the network, and in each section of the network, the resolution is the same. And after each pooling layer, we reduce the resolution by a factor of 2. Now, we want our models to be ReLU balanced, which means that after each pooling layer, we want to quadruple the size of channels. So, so this is one of the design rules that we introduced. And then the only thing that remains is finding the number of channels for the first layer, which we can compute based on the ReLU budget that exists. So these base networks are defined for a given depth and a ReLU budget, and then you can design it. Now, once we have this set of base networks, then we can run ENAS over them to find the operations at each layer, let's say 5 by 5 or 3 by 3 convolution, and also the placement of these skip connections. Okay, so let's look at some of the results that we get. First, looking at the base networks compared to networks that are ReLU pruned or shuffled. So as I mentioned before, this ReLU shuffling doesn't change the functionality of a network, but for these 3 models that we experimented with, can actually drastically reduce the number of ReLUs just by shuffling. And then pruning further reduces the number of ReLUs in that network, which would change the functionality and potentially affect the performance of that model. But it turns out that for smaller ReLU budgets, this would allow you to design networks that are larger. Let's say you can scale them in width, and that would result in better performing models. So for the first model, the ReLU pruning would actually give you a better performing model. Additionally, comparing this ReLU balancing to flop balancing and a strawman channel balancing, which is keeping the same number of channels at each layer, you can see that for the same ReLU budget, let's say here it's a budget of 86 number of ReLUs, the ReLU balancing actually is going to give you the best performing models. And you can see that these models that are ReLU balanced have more parameters compared to the other classes. But because we only care about the number of ReLUs as a ReLU budget, this is something we can do. So in order to get the best performing models for a ReLU budget, you want to have this rule of ReLU balancing. And finally, comparing the models that CryptoNAS can find with existing families. So we designed 3 base models, CNET 1, 2, 3, with depth of 6, 12, and 24. And then you can scale each of these models in width depending on your ReLU budget. So that's how we find models across different budgets. And we are actually able to get the best models on this Pareto frontier compared to different classes such as DenseNets, ResNets, and even compared to models such as MobileNet, which are designed for constrained devices, right? So this basically the take home here is that the take home message is that if you're looking at private inference or private computations, the needs of the models over there are completely different from the models that exist in clear text. And even architecture search methods have to be adopted to be able to perform best for this class. Okay, so this is the work that we did for designing networks. Now I'm gonna talk a little bit about another work that we did previously, and in this case we're looking at verifying outsourced computations. So let me make the setting clear. So in this case, you have a client that is going to outsource an inference computation. So the client has a model and an input, and wants to and doesn't have the computational or energy resources to perform this inference, and wants to outsource this computation to a server. Now there are different reasons why the client wouldn't trust this server to return the correct result. The server can be malicious, inject misclassifications. It could be compromised, or it could replace the model with a less accurate one just to reduce its computational load. So now the question becomes, how can the client ensure that the computation was done correctly without redoing the computation itself again, because that would not motivate the outsourcing in the first place. And this falls under a very active field of verifiable computing. An example of it is interactive proof protocols. And in this case, you have two entities, a prover and a verifier. Where the verifier is asking a question, the prover is responding to that question. And then after that, the prover and the verifier are going to have a conversation during which the prover wants to convince the verifier that this computation was done correctly. Basically, this answer was correct. In this case, it's a computation. So the requirements here are that an honest prover must be able to convince the verifier to accept this result. And a verifier should be able to catch a line prover with high probability. So, usually this is a very large number. So these are a class of probabilistic proofs, per se. So a building block in these proof protocols in probabilistic proofs is a protocol known as the sum check. And I'm going to go into a little bit of detail because this is the main component of how we design these protocols for outsourced neural networks. So in the subject protocol, the claim that we want to verify is the evaluation of a polynomial over a field. So let's say we have this G polynomial defined over 3 variables, and the evaluation of this polynomial over all binary values is claimed to be Y. So let's say a verifier is outsourcing this computation and then wants to verify this result. And this looks a little bit arbitrary, but I'll later show how this evaluation, if we are actually able to do this, if we are able to verify such a computation, then we can expand this to more interesting and more useful types of computations that show up in a lot of applications. Okay, so in this protocol, what the verification is done over a number of steps. So at each step, the prover is going to compute a univariate polynomial by evaluating that polynomial over all but one of its variables. And there's a back and forth between the prover and verifier to verify this claim. So in the first step, what the prover is going to do is create this polynomial h1 of x1, which is evaluation of g over all but one of its variables, and send this over to the verifier. Now, what the verifier can do is to check the claim. Basically, this should hold if I compute h1 0 plus h1 1, this would be the original claim, right? So this should be equal to y. If this is correct, the verifier is going to sample a random value from the field, send this to the prover. The prover would replace the first variable with this random value and do the same thing, in that it would generate another univariate polynomial by evaluating all but one of its variables over binary values. So this is h2 of x2, send this to the verifier. Now the verifier can do another check at h2 0 and h2 1 and check that it's equal to h1 r1. You can see that you can check that this should hold if the prover is telling the truth, and so on and so forth. So at the very last step, the prover is going to return a polynomial over x3, And then the last check for the verifier is basically evaluating this, the last polynomial over a random value and checking that it should be the original polynomial over all the random numbers generated. And if all of these checks hold, then the verifier can be sure with high probability that this is correct. So at a high level, what this protocol does is for the verifier to do these checks is very easy, right? So these computations are can be done in constant time, and the last step is just evaluating the polynomial at a random point, right? So this is the work of the verifier here. Now compare this with the original computation, which was in this case 2 to the 3 evaluations of this polynomial, right? So on the verifier side, we've reduced this computation significantly, and now with high probability, the verifier can check this function without having to do it. Okay, so now that we have this protocol, we have a protocol, an interactive protocol that can enable us to, or enable a verifier to verify a claim of this shape. And what we want to do is see if we can transform other interesting computations into this format and then use the sum-check protocol to verify it. So one very useful type of computation is matrix multiplication. And Justin Taylor showed that you can use the sum-check for verifying this. Actually, you can do one round of sum check and verify the matrix multiplication as a whole. So now here our goal is again to transform this computation into a format that can be verified by sum check. So let's see how we can do that. In this case, we have a verifier with 2 matrices, A and B, is outsourcing this to a prover, let's say, and the prover returns the result as C star. And the verifier wants to verify that this C star is actually C, the multiplication of A and B, without having to do the multiplication herself. So the first step is to interpret these matrices as functions. So you can define a function over I and j binary values, which would basically for, let's say, for I0 and J0 would give you the first element of the matrix, and so on and so forth. And then what you can do is extend these functions, these are called multilinear extensions, of this function into a field. So what it means is that now this function is defined over x and y, which are which belong to the field, and for the binary values, this would give you the same function. And now what we want to do is we want to ensure that the evaluation of the resulting matrix interpreted as a function is the same as the actual result. So we verify this matrix multiplication by evaluating basically the verifying these 2 evaluations are the same. So you can think of it as basically if I have a matrix, instead of evaluating each of these elements by itself, I am kind of looking at a linear combination of all of these, and I want to verify that one value. So you can think of it at a high level like this. So in order to do this, what we can do is write the matrix multiplication in this format. You can verify that this is correct if C is A times B, and then extend this to the field. So essentially what we've done here is that the expression here on the right is the same as we've seen in the sum-check protocol, right? So what we've done is transform this computation into a format that can be verified using sum-check. So that's the basic idea. And the verifiers, majority of the verifiers work at the last step would be to verify each of these A and B matrices, which the verifier has. Those are the inputs, right? So now instead of doing a n-cube work for the verifier to do this computation, the verifiers only has to do n-squared. So this is how the computation is reduced. Okay, so these are the tools that that exist. Let's step back a little bit and look at neural networks and how we can use these tools to verify computations of a neural network. So the first insight that we have in SafetyNets is, well, you can basically use matrix. You're essentially doing matrix multiplication in the linear layers, right? Usually, inferences are performed over batches of inputs, so you're multiplying a weight matrix with an input matrix. So this can directly use the Thaler's matrix multiplication protocol for verification. Okay, so that's good. Now let's look at nonlinear layers. So in this case, we propose to replace the nonlinearities with quadratic functions. So we're using x squared as a function for nonlinearity, and you also have to ensure that all the computations, all the elements or the weights and activations have to be within a field, right? Okay, but how do we even verify? We have a protocol for matrix multiplication. We don't have a protocol for quadratic activations, and that's something we proposed, an interactive proof protocol for this quadratic functions, and the underlying idea is the same. You want to transform this function into a format that can directly use the subject protocol. So if you look at a quadratic, this is like element-wise squaring of each value. Again, you can interpret it matrices as functions, and then finally transform it into an extension into a field. The details are not very important. What I want to emphasize is that you have to basically introduce some auxiliary functions, but then you are able to eventually turn this computation into a format that can directly use the subject protocol, right? So now we have these pieces. We have a protocol for verifying matrix multiplication. We have a protocol for verifying quadratic functions, and we want to put them together to have an end-to-end verification protocol for neural networks. Okay, so let's take a look at how we basically compose this end-to-end verification. So an example here is two-layer neural network. In the first layer, multiplying the inputs with the first layer weights, and then the quadratic activation, and then the last layer weight multiplication. Now, in the output here, you're getting this matrix Y1, and you want to verify that this matrix is the correct result, right? That's what we want to do. Again, instead of, so this is something proposed by, basically this composition, we use the same format as a method that was proposed by Goldwasser et al. The idea here is that instead of verifying this matrix element by element in a kind of a non-very accurate way, you can think of it as verifying a linear combination of all of them. So what I'm going to do is, quote unquote, generate a linear combination of all of this, which would give me a value, and I want to verify that claim, that one claim. And that is a claim on the output. And we are going to do this composition going backwards. So I am going to transform that claim on the output into a claim on the outputs of the layer before. So if this claim on the output is correct, then the claim should, from the previous layer should be correct, and so on and so forth, until I reach the input. So I want to turn this claim on the output into a claim about the input that the verifier can check for themselves. So let's see how we do that. So we start with a claim on this Y1 matrix. As I said, you want to quote unquote verify a linear combination. So this evaluation of the extension over random values, that's what it is. And you want to, what you're going to do is use the matrix multiplication protocol, the sum check over matrix multiplication, to transfer this claim into a claim of the inputs, which is the weights of the last layer and the inputs of the last layer. Now, the verifier can compute the claim on the weights because they know the weights. How do they verify the claim on the inputs of the last layer? What they're going to do is use the quadratic protocol that we introduced to transform that claim into a claim about the layer before. So you're going to do this until you reach the very first layer where you're transferring the claim of the output of the first layer into a claim about the weights and the very inputs, right? So both of these are things that the verifier knows. So the verifier provided the input so she can compute this claim on the input. So basically, what happened was for the verifier, all they need to do is compute these claims on the weights, which the verifier has the model, so they can do it, and also a claim on the input. Again, the verifier has the input, so they can do it. So we transferred this computation, verifying of this whole computation into these blocks and verifying each part and going to the input. Okay, so I'll just show a little bit of what it looks like to generate models. So the first constraint was that you would have to train networks with quadratic activations. In this case, we've trained networks over MNIST and timid speech recognition, and in later work we've also trained AlexNet over Tiny ImageNet. There's a little bit of you have to be careful when you're training quadratic networks. You have to probably use tricks such as gradient clipping to make sure that the networks converge, but eventually you can achieve the same accuracy. And the other constraint is that you have to ensure that the values are within a field. So in all of these protocols that I discussed, the values were within a, let's say, a prime field, right? So what you want to do is to quantize, not during training, only during inference, the weights and activations in your network. And also ensure that the maximum value in your network does not exceed the field, right? So if you have a field of size, let's say to the power 64, let's say, you don't want to, you want to make sure it doesn't exceed that. So given these constraints for this networks that we trained with, we were able to achieve similar, or even better accuracies for these tasks. And finally, if you compare the runtime of outsourcing for local computation, verifier, and prover. So in this case, this is a network, fully connected network that was trained for this speech recognition task. And compared to the original computation, let's say for a batch size of 2 to the power 10, the verifier's work is about 150x less than the computing the function locally. So one one thing to point out here is that these protocols benefit from batching. So in order to benefit from outsourcing, you want to do this computation over large batches. And then the additional provers cost for doing this is around 5%. So in addition to the computation, the prover has to do an additional 5% work to provide these proofs for this computation. How much time do I have? I can go or I can stop here and take questions.
I mean, we have 10 more minutes, right? Right, Jamie?
Yeah, about 10 more minutes.
Okay, cool. So I'll because now we have time, I'll go over basically some of the work that we did extending this. So this verifiable protocol that we developed was for fully connected networks. And if you want to represent convolutional networks, which are very, very common, you would have to transform them to matrix multiplication, to fully connected layers. But then this results in large matrices. For example, for Alex, it was like 1 terabyte of memory. And also the other thing that I mentioned was that these protocols would have to use batching to benefit from outsourcing. So in extending this work, we aimed for finding verifiable protocols specifically for convolutional computations. So the idea is, again, transforming these convolutional computations into the original sum check format instead of transforming them into a matrix multiplication. So looking at the how you construct the convolution, we can write each element in the output as basically this dot product of the weights and input. And then if you generalize it for x and y, then you have a equation of this kind. Basically, you're summing over all the block of the weights, right? And then finally, the generalized convolution over C in a number of channels, input channels, and C output channels, right? So in this most general format, you have an expression of this kind. Now, if we were to use sum check for this is not exactly in the format that we're familiar with. And our contribution here was to essentially take this expression and introduce, basically transfer it into an expression that can be used, that can be verified with sum check. And without going into a lot of details, we basically introduced some auxiliary functions to help us do this. And at the end, if you look at the final expression, this is a format. The goal here is just to transfer this convolution into something that we can use sum check for, and that's what we did. And now, if we compare this protocol that we developed, so this is the convolutional verifier compared to the original fully connected verifier. This is for a convolutional network that is to be trained over MLaaS digit recognition. And you can see that the verifier for the convolution does not require batching anymore. So even for a batch size of 1, you can still benefit. This is like almost 100x faster. You can still benefit from outsourcing. And additionally, the prover of this convolutional protocol is faster than the fully connected protocol. So these are the benefits that we can gain by this developing this specialized protocol for convolutional layers. And a little bit about some of the work that we're currently looking into. So in the first work, we were looking at designing networks for private inference, right? And instead of looking into optimizing these cryptographic protocols, which is the work that was done so far, we looked at how can we design better models for these existing protocols. And now we are basically looking a little bit more carefully at these protocols that are used for computing different parts of the neural network privately. So this is part of the future work that we're looking at. Basically, the protocol for evaluating ReLU layers is the idea is that in order to verify, in order to compute a neural network as privately, the server and the client are going to hold secret shares of each layer. So at each layer, the server holds one share of that layer's value, and the client would hold another share. And what happens at the ReLU layers is they construct this circuit to compute the ReLU function, which is adding these two shares together and then computing the ReLU. Now, the circuit to do this is actually quite complex, and that's where a lot of the overhead comes from. So for one inference in ResNet, you can see that it has to store around 8 gigabytes just for this circuit. This is part of the Decouple circuit. And our proposal is to change this computation. Instead of computing the ReLU, we can compute, we can express it differently, basically multiplying x with the sign of x. Sign of x is, if it's positive, let's say it's giving 1. So this effectively gives you the ReLU function. Now the multiplication computation can be done without using Decouple circuits, right? And all you need to do is basically use a circuit for computing this sign function, which is going to be smaller. So we were getting 3.5 reduction in size, which directly translates into reductions in computation and communication for the bottleneck. Okay, I think I want to stop here and take any questions.